Problem number 3, find the first 3 non-zero terms of the Maclaurin series of tangent of x. I'm going to show a couple of different ways to solve this problem in this video of differing difficulty and ease and stuff like that. So the first thing that pops into your mind when thinking about Maclaurin series is probably just going to the definition here. That's saying our Maclaurin series is the sum from n from 0 to infinity of the nth derivative of f evaluated at 0 divided by n factorial times x to the n. And so if we can find a nice easy pattern to the derivatives of tangent x, for example, then we can very quickly easily do this. For example, if the function is e to the x, we know all of the derivatives are just e to the x themselves. If it's e to the 3x or something like that, it's just going to be powers of 3 times e to the 3x are the derivatives. Sines or cosines, we know we have loops and stuff like that. So the first thing that pops into our mind is probably just to compute a bunch of derivatives and hope for the best. And so I wrote them. I computed the derivatives out to the 5th derivative here of f of x. And as we can see, this is just a mess. So from this, we'll be able to write down the answer. And I'll do this, but I'll just point out, this is not something you'd really want to do by hand. When I wrote all these stuff out, trust me, I was using a computer to do all these calculations for me to make sure I wasn't, making any mistakes here. Yeah, how do you go from 8 tangent x secant squared x times tangent squared x plus 2 secant squared x? That's going to be an awful lot of product rule and chain rule to go from here to here. Not something I want to do without a computer. But if we've already have done this, then we can say, well, we care about evaluating this at 0 here. So f of 0, tangent 0 is 0. F prime of 0 is going to be secant squared of 0 is 1. F double prime of 0, 2 times tangent 0 is 0. I can ignore that to 0. F triple prime of 0, secant is 1. Secant 0 is 1. Tangent 0 is 0. So we end up with 2 times 1 plus 0. 2 times 1 times 0 plus 1. That's 2. The 4th derivative of 0, tangent 0 is 0, so that makes this whole thing 0. And the 5th derivative of f at 0, 8 times 1 times 0 plus 2 plus 0. And so that's going to be 8 times 2 is 16. Okay, so 0, 1, 0, 2, 0, 16. It said the first 3 non-zero terms that I need are going to be given. So I have to go all the way out to the 5th degree stuff. So this is going to become, let's see here. So 0 plus 1 divided by 1 factorial times x to the 1st. Plus 0 divided by 2 factorial x squared, plus 2 divided by 3 factorial times x cubed, plus 0 divided by 4 factorial x to the 4th, plus 16 divided by 5 factorial times x to the 5th. That's how this is going to start. And if you simplify this down, you get x plus 1/3 x cubed plus this simplifies down to 2/15 x to the 5th. Okay, so I just spent the first, we're at 4.5 minutes in. I just spent the first 4 minutes or so of this video talking about an approach I really don't recommend. This is more just to illustrate how, the natural way to do it, the naive approach to do it, but it's not the best approach. So let me show a better approach to use. And this will be the fastest one. It's going to be rewriting tangent x as sine x and cosine x. Well, let me do that right here. We know that tangent x is sine x divided by cosine x. And we know the Maclaurin series for both sine x and cosine x. So we shouldn't want to reinvent the wheel here. We should want to make our lives as easy as possible. So sine x, it starts off x minus x cubed over 6 plus x to the 5th divided by 120. Cosine x starts off 1 minus x squared divided by 2 plus x to the 4th divided by 24 minus dot dot dot. All of the omitted terms that I have here are going to be of degree higher than x to the 5th. And we can see here we only need to go out to x to the 5th. We're going to aim for this much, much more simply. So we're going to divide x minus x cubed divided by 6 plus x to the 5th divided by 120. We're going to divide that by 1 minus x squared over 2 plus x to the 4th divided by 24. So let's do that on the next piece of paper here. So it's going to be long division here, but note I'm writing things maybe backwards from what you're used to. Usually when we do polynomial long division, we write the higher degree terms on the left and the lower degree terms on the right. But here I'm writing them in reverse order. In some sense, the higher degree terms are the less important ones. Usually we think of higher degree terms as the more important ones. Okay, so let's get to work on this long division. So how many times does 1 go into x? X times. And so we're going to copy down, multiply this by x, and we get x minus x squared divided by 2. Sorry, that should be x times x squared divided by 2 is x cubed divided by 2, plus x to the 4th divided by 24 times x is x to the 5th divided by 24. And we're going to subtract this from this right here. And we end up with x minus x is 0. X cubed minus x cubed divided by 6 plus x cubed divided by 2 is x cubed divided by 3. And x to the 5th divided by 120 minus x to the 5th divided by 24 is, I'm going to skip the crunching out the fractions here and just write down the answer, minus x to the 5th divided by 30. Okay, what's next? How many times does 1 go into x cubed divided by 3? Well, that's just x cubed divided by 3. Going to multiply this by x cubed divided by 3, and we end up with 1 times this is x cubed divided by 3. X cubed divided by 3 times minus x squared over 2 is minus x to the 6th divided by 3 times 2 is 6. Oops, that's minus x to the 5th. X squared times x cubed is x to the 5th. So now we're going to subtract this minus this. And by the way, and we end up with 2x to the 5th over 15. By the way, I should point out that I didn't bother multiplying x to the x cubed divided by 3 times x to the 4th divided by 24, because that would give us an x to the 7th term, and that's farther out than we care about. We're only going out to x to the 5th terms. And so similarly, how many times does 1 go into 2x to the 5th over 15? That's just going to be 2x to the 5th divided by 15. And we're done at this point. And we can see that we ended up with the same exact answer here as we did in this case, but a lot more simply. We did it without doing all of these derivatives that you just do not want to do by hand. So this is a process that you can actually carry out by hand, so that makes it better than this process for examination purposes, because you can't, on examination, you can't just go to Wolfram Alpha or something like that, which is what I did, and ask it for the first 5 derivatives. Okay, so this is the solution of the problem. If you want to stop watching the video here, that's a completely reasonable thing to do. I'm just going to show one more thing, one more approach, which is the first thing that popped into my mind when I saw this problem. I think it might be a little bit longer than this, but it illustrates some different concepts. So you may want to keep watching, or you may just want to call it wraps here. So the approach that I'm going to do for the final one, the final part here, is I am going to find a series for 1 over cosine x, which of course we know that's secant x. And then once I find a series for 1 over cosine x, then multiply the series for sine x times, so with the series for 1 over cosine x. So if dividing power series is something that we're unfamiliar with, multiplying two power series together to get the first, out to the x to the 5th terms or so, that is something that we should be familiar with. Okay, so how do I go about finding a series for 1 over cosine x? Well, I know that cosine x, it starts off 1 minus x squared over 2 plus x to the 4th over 24 minus ... These are all the terms we need. We're only going out to x to the 5th. And so 1 over cosine x, I don't know what it is yet, so I'm just going to write down placeholder stuff. It's a0 plus a1x plus a2x squared plus a cubed x cubed plus a to the 4th x to the 4th plus a to the 5th x to the 5th plus ... This is just a generic series, and I'll try to figure out what the coefficients are later. And when we multiply these two together, we should get 1. Cosine x times 1 over cosine x should give us 1. Okay, so what we're going to do is that we're going to set up lots of systems and equations here to figure out what a0 is, what a1 is, what a2 is, what a3 is, by comparing coefficients of different powers of x here and here. Basically, what's going to happen is that when we multiply this through, every power of x, at least 1, is going to have coefficient 0, because that's what happens on the left. Okay, so how do we start tackling this? The constant term, the only way we can get a constant term on the right is by doing 1 times a0. Everything else is x's in it. And so the constant term on the left is 1. The constant term on the right is 1 times a0. And so at this point, we know that a0 is equal to 1. How about the coefficient of x to the 1st? The only way we can get x to the 1st here is by doing 1 times a1x. So a1x times 1. And let me just look at the coefficient here, a1. The coefficient of x to the 1st on the left is 0. So this tells me that a1 is equal to 0. So think about coefficients of x squared on the left. As always, it's going to be 0. When we do x cubed, x to the 4th, x to the 5th, those are all going to be zeros. What's the coefficient x squared here? How can we come up with it? 1 times a2. So that's a2. And minus x squared over 2 times a0. So that's minus a0 divided by 2. But a0 is 1. So a2 minus 1 half. a2 minus 1 half has to equal 0. So that tells me a2 is 1 half. So far we know our series. We can be more particular here. It's going to start off 1 minus 1 plus 0x plus 1 half x squared. We've got the first several terms of the series for cosine x. If we keep going, x cubed, so coefficient x here over here is 0. And the only way we can get x cubes here is by doing a1x times minus x squared over 2, a1 times minus 1/2, plus a3 times 1. But this is 0, so a3 plus 0 is equal to 0. a3 is equal to 0. X to the fourth now, the coefficient over here is 0, and there's 3 ways that we can make x to the fourth here. X to the fourth times divided by 24 times a0, so that's a0 divided by 24, minus 1/2 times a2, and plus 1 times a sub 4. So plugging in a0 and a1, a0 and a2, we have 1/24 minus 1/2 times 1/2 is 1/4, plus a4 is equal to 0. So that tells us a4 is equal to 5 over 24. If we do x to the fifth, I'm going to skip the details and just say a to the fifth ends up as 0, so we can stop here. So what this tells us is the first several terms of 1 over cosine x, that's secant x, are 1 plus 1/2 x squared plus 5 over 24 x to the fourth. And so we end up with sine x times 1 over cosine x. This starts off as x minus x cubed divided by 3 factorial plus x to the fifth divided by 5 factorial times 1 plus 1/2 x squared plus 5 over 24 x to the fourth. And when we expand out this multiplication, x times 1 is x plus 1/2 x cubed plus 5 over 24 x to the fourth. Everything else is terms higher than, degree higher than 5, so we don't care about them. Minus 1/6 x cubed minus 5 divided by 6 times 24. I'm getting thrown off here. I should be multiplying this times this, so that is minus 1/6 x cubed. Now I multiply this times this, and I have minus 1/12 x to the fifth. This one, the power is too high. And then I have plus x to the fifth divided by 120 from multiplying here. The degree is too high. And when we add all of these up, sure enough, we once again get the same exact thing as earlier, which is x plus x cubed over 3 plus 2x to the fifth divided by 15. So interesting problem, tricky problem, and I gave you 3 different ways to solve it.